the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. The solar system. How did it emerge from the oblivion of interstellar chaos?
We are made of gas and dust.
Today, the sun and planets hold fascinating clues to their origins in a haze of particles so small, they're virtually invisible.
The evidence of our past is all around us.
But are the titanic forces that created our solar system common throughout the universe? Or are we unique?
Our solar system seems to be one of the oddballs.
The universe may have countless strategies for crafting stars and planets, but only one could determine how the solar system was made. It begins at a point in time nearly 4.6 billion years ago. A giant cloud of gas and dust floats eerily through a remote arm of the Milky Way, chilled to more than 400 degrees below zero.
When it's sitting there all alone, nothing much is happening in a molecular cloud. The temperatures are very low, the particles are moving around very, very slowly. It's just sitting there. But if you have a nearby supernova, an exploding star, it can send a shock wave through this molecular cloud, triggering its gravitational collapse.
That collapse is the first step in a long process that brings the place we now call the solar system into existence. Our mission now will be to follow a timeline of the first 700 million years, the epoch in which the solar system formed and stabilized. We start by looking at the sun and its planets as they are today.
The evidence of our past is all around us. The 4 planets in the inner part of the solar system are made of rock and metal, and the 4 planets in the outer part of the solar system are these giant balls of gas. So clearly different processes were at play, and that tells us something about how we got here.
We learn the story, as scientists presently believe it happened, from time zero, the very beginning of our solar system. The supernova explosion not only seeds the giant gas cloud with heavy elements like iron and uranium, the jolt of the explosion gives the cloud a push into the future as wave fronts compress the cloud's gases into a critical mass.
That mass begins to collapse under the force of gravity, and then it's unstoppable. It's rapid. It's irreversible.
It's like a roller coaster reaching the top of its track and speeding down the other side. The collapsing cloud, destined to become our solar system, becomes a virtual theme park of chaotic motion.
An amusement park like Knott's Berry Farm is a great place for people to come and experience the kind of motion that happens in the early solar system. There's gravity, there's collisions, momentum, forces. All of those interactions that took place in the early solar system can be found here on all the different kinds of rides.
Those interactions intensify in the rapidly collapsing cloud, where gas and dust contracts into dense pockets. Each will become the nursery of a star.
When the giant molecular cloud was triggered and started to collapse, a lot of other protostars and a lot of other solar systems were formed at the same time. So our sun actually has a lot of brother and sister stars that formed right around the same time as the sun.
The first stages of our solar system's creation are hardly unique. Today, we witness the same thing happening in the Orion constellation, where a giant molecular cloud stretches hundreds of light years across. In some places, collapsing pockets are now forming clusters of young stars, which light up the surrounding gas. The circus of motions in the amusement park aptly parallels the movements of space matter that comes together to make the solar system. The most basic of these motions is circular, like a celestial carousel. As the pre-solar cloud collapses, we begin to notice its rotation, a spin that has actually been there from the beginning.
The entire galaxy rotates. Everything in the galaxy rotates. Everything is rotating with respect to everything else. And so rotation is part and parcel of the physics of stellar collapse.
What happens next resembles a spinning ice skater. When she draws in her arms, she spins faster. As gravity draws in the cloud's gas, the cloud not only spins faster, it inevitably flattens into a disk. We can see a similar process at work on Earth, in places like Joe Cariati's glassblowing workshop in California, where astronomer Laura Danley is observing the action. Joe begins with a round blob of red-hot molten glass.
We basically just are taking a solid mass that was round and spinning it.
It flattens because it's much easier for the fluid of this liquid glass, to collapse in the same axis, along the axis of spinning, rather than try to fight the spin or fight the angular momentum and move closer. And just like in our solar system, if there were planets forming in there, they'd all be in the same plane. It's just like the disk of our solar system. Now, it looks kind of elliptical. It's not circular. We think of our own solar system as being circular, but I think you told me it had to do with there being more mass on one side. So maybe it's kind of like an analog of a binary star forming, where you've got maybe extra mass on one side that's also going to form into a star or a brown dwarf, or maybe just a very massive Jupiter-like planet. It's so tempting to touch it, but I'm actually...
Oh, no, we can't do that. Yeah, we can't do that.
100,000 years after it began, the cloud that will become our solar system has almost entirely collapsed, and its center is glowing with the radiance of an emerging protostar.
A protostar is the very earliest stages of becoming a star, is when the star is still collapsing down and the energy that it's radiating out is coming from that gravitational collapse. It's still getting hotter because it's getting smaller. It's not doing the nuclear reactions like a star will be doing when it's in its main phase of being a star.
The emerging protostar begins gobbling up the disk of gas and dust that makes up what's called the solar nebula. So much of it will end up in the sun that what's left over for the planets, moons, asteroids, and even our own bodies is so meager, it's almost a cosmic afterthought.
We happen to live on a planet, so the stuff that went into making the planet is very important to us. But it was just a tiny part of the whole mix. This parking lot is a good way of showing how tiny. When you look at the solar system today, the sun is 99.85% of the total mass. So compared with the 500 cars in this parking lot, my car is just about all that's left over for all the planets, asteroids, and moons. And as for the Earth itself, well, that might be comparable to this spare tire, nothing bigger.
At 1 million years after time zero, the solar system's method for sorting out its planet-building material is clear. They're separated by the different temperatures in the disk. Close to the protosun, temperatures above 2,000 degrees vaporize everything. But about 5 million miles out lies the rock line, where it's cool enough for metals and minerals to turn solid. Much farther out lies the snow line, where it's as much as 375 degrees below zero. Cold enough for water, methane, and ammonia to freeze into ices.
The early solar system is a little bit like making cotton candy. And to show us how cotton candy's made, we have Kathy Wu here to make us a delicious treat.
First, we take the sugar crystals and we pour that into the heating element.
So the heating element in this case is here in the center. In the case of the solar system, of course, it's that very hot sun in the middle that's melting things that are too close to it. And as that hot sun heats up, it starts to melt the stuff that's close to it. Oh, there it comes. This is now the solar nebula you can see flying around here. On the inside, you actually don't see anything. The inside, it's all molten, and as it gets to the cooler outside, the solar nebula starts to condense, and you can see it starting to solidify all over the outside of the solar system where it's cold. You get a line of gaseous stuff on the inside and the solid stuff on the outside. This is also a very good analogy for what those early protoplanets are like. They start to accrete by all sticking together, very much like this cotton candy does, and make larger and larger things coming from these tiny little pieces of crystal that are the sugar that's in the cotton candy. Thank you. The solar system is delicious.
The particles sticking together are microscopic at this point, far smaller than the melting sugar crystals. And as cotton candy illustrates how these solids accrete in the solar system, another amusement park attraction shows what makes them grow. Bumper cars wouldn't be much fun without collisions. And in the solar system, without collisions, there would be no growth, no accretion.
The accretion collisions that were happening in the early solar system are of the kind that allow objects to stick together through various kinds of essentially friction-type processes where you have things getting stuck together just due to mechanical interaction.
In the inner solar system, the process is time-consuming, as tiny cosmic dust balls form slowly, stuck together only by random collisions in their orbits around the early sun. But in the outer solar system, the story is dramatically different. The giant planets are about to burst into existence in a cosmic blink of an eye. Beginning as a cloud of gas and dust, the making of our solar system will take 700 million years. Now, just 2 million years after its birth, the young system takes its first steps in creating a family of planets that one day will be as diverse as Jupiter, Saturn, or the Earth. For now, though, they are chunks of matter continuing their roller coaster ride in the turbulence of the solar nebula. The thick, rotating disk, made mostly of hydrogen gas, is embedded with solids. The inner zone is filled with small chunks of rock, but outside the boundary known as the snow line, there are also ices of methane, ammonia, and water, which dominate the outer disk, and for good reason.
They're all hydrogen compounds of one form or another, and hydrogen is the most abundant element in that region of the solar system at that point. That abundant hydrogen is combining with elements such as oxygen to form the water, or carbon to form the methane, or nitrogen to form the ammonia, and giving us those compounds which are then freezing out.
Continual collisions amid the turbulence make tiny specks of dust and ice stick together through friction and static electricity until they're large enough for gravity to take over. Eventually, they become planetesimals.
Planetesimals were the original building blocks of our solar system. They're incredibly small, only about half a mile to a mile across, but there were countless numbers in the early solar system. It was simply littered with them.
These half-mile planetesimals will eventually form full-scale planets, but of distinctly different sizes. That's what Ryan Chan of San Mateo, California, wanted to ask the universe by writing, why are the planets closer to the sun smaller than the giant planets farther away from the sun?
Ryan, the inner planets are smaller than the outer planets because the inner planets didn't have much material from which to be made, just metals and rocks and things like that. The outer planets, after forming an Earth-like core, were able to attract ices of water, ammonia, methane, and carbon dioxide. That made them get bigger. And then they gravitationally attracted gases, becoming much, much bigger.
"3 million years after time zero, planetesimals are merging into bigger objects called planet embryos, or protoplanets.
Protoplanets are built up of planetesimals, so they're larger, about the size of our moon.
Just beyond the snow line, where ice is most abundant, the teeming mob of protoplanets collide and fuse in a frenzy of planet building. Within just 3 million years, these collisions give birth to a frozen young planet destined to become the monster of the solar system, the infant Jupiter.
Before it became a giant planet, Jupiter was sort of like a super Earth, maybe 10 or 15 Earth masses.
The early Jupiter is made of rock and ice and continues to grow. At a crucial moment, one last protoplanet slams into its surface. It's another roller coaster-like tipping point in the making of the solar system. The added mass sends Jupiter over the edge to become a gravitational bully.
After it reached a certain critical mass, Jupiter's gravity was able to very quickly draw in material, sort of a runaway effect that made it very large, very fast.
Like a cosmic vacuum cleaner, Jupiter sweeps up virtually all the gas in its orbital path, growing to 90% of its present size in just 100,000 years. Saturn, Neptune, and Uranus, in turn, follow Jupiter in devouring enough gas to become gas giants. The dramatic sweep of one or more planets clearing a lane through a disk around a star is thought to be common in the universe, a fact borne out in recent telescope discoveries.
We see this process happening in other solar systems being formed as well. We're finally at the point where we can image other disks around stars and the gaps that are being created by the large planets that are orbiting them.
In early 2011, astronomers using the Subaru telescope in Hawaii released a photograph of a star 450 light-years from Earth. An advanced optical mask allowed them to block out the light of the star itself, revealing the first direct image of a disk with zones cleared out by orbiting planets.
That's a really amazing high-resolution image that shows a disk of gas and dust around a star, and the inner parts have been carved out by one or more planets that have accreted material and also flung other material away.
3 million years along the timeline, Jupiter and Saturn are now the titans of the solar system. The two giant planets will eventually contain 92% of all the non-solar mass in the entire system. 10 million years into its life, the young solar system is virtually out of gas. In this case, the gas is the hydrogen and helium that fueled Jupiter and Saturn's swift growth.
The forming star had this huge solar wind that was clearing material out of the solar system. Jupiter and Saturn were fortunate enough to pick up most of this material in their orbits, which is why they're so large. Uranus and Neptune were a bit later to the game and were unable to pick up as much material, which is why they're smaller than Jupiter and Saturn.
During the time before the dust and gas were blown away, the forming solar system was largely hidden from the rest of the universe. Even as dust and gas were forming planets, the disk remained thick enough to block light from the protosun at the center.
At a distance of several Earth distances from the sun, for example, looking back towards the sun, in the earliest phases of the solar system, we wouldn't be able to see the sun. We wouldn't be able to see the visible light.
What would the early solar system have looked like to alien astronomers gazing at us from even greater distances? The Hubble Space Telescope shows us with photos of protoplanetary disks in a star-forming region 1,350 light-years from Earth.
We can see them at a variety of angles, tilts, relative to our line of sight. For example, if they're face-on, we can see a central star surrounded by a disk. But when we look at these objects edge-on, the gas and dust that is between our line of sight and the central star blocks the light of the star.
But now, 10 million years after the solar system began to form, with the dust and gas virtually gone, the sun-to-be shines brilliantly through space. It has yet to go through the process of becoming a true star, and at this point, it would seem strange to modern eyes.
The spectrum of light was very different, so it was putting out a lot of energy just as it does today, but it was actually much redder in its spectrum, so that early solar system would have been a very different color from what we see today.
The protostar, orange-yellow in appearance, is a seething cauldron. In some systems, the cores of contracting clouds never glow with anything more than the dim light of dull brown dwarfs. Our early sun now nears a critical point. Will its internal furnace sputter and fail? Or will it breach the nuclear threshold and shine across the galaxy with all the brilliance of a true star? We are now at the most critical point in the making of our solar system. At 50 million years old, the protosun and its forming planets are barely 1% of their present age. In many systems, the central star doesn't have enough mass to fully ignite. But our sun is about to overcome that fate. It has reached the critical threshold of heat and pressure, where nuclear fusion can begin at its core. Using the same awesome energy that powers the hydrogen bomb, our sun bursts into life as a fully formed newborn star.
At about 50 million years into the life of the solar system since it first began forming, the sun goes into a different phase, burning hydrogen, actually doing nuclear fusion. At that point, the sun becomes what we think of as now a fully fledged star.
Nuclear fusion will carry the sun into the distant future. It will burn long enough to support the evolution of life on Earth, shining unceasingly for about 10 billion years. Unlike the newly nuclear sun, the rest of the solar system is far from mature. 40 million years earlier, the frozen gas giants outside the snow line ceased to grow and achieved an icy stability. But in the hot inner solar system, where gas is rare but rocks abound, chaos still reigns.
By the time that the sun has become a full-fledged star, the planets in the inner part of the solar system are still trying to grow. There are small little protoplanets that are building together, colliding, getting larger and larger, eventually to become those 4 big planets that we have in the inner solar system.
But just inside the orbit of Jupiter lies a narrow region where the smaller planetesimals rule, and protoplanets are rare. This is the asteroid belt, where Jupiter stirs things up to prevent any planets from forming.
Jupiter is the largest planet, and so its gravitational influence is the greatest in the solar system. There was a point in the early solar system where Jupiter was passing through what's now the asteroid belt, pumping up the velocities of the planetesimals there, causing them to collide in a destructive manner. They blew apart. We're going to try to get a feel for what a destructive collision is like in the asteroid belt, but we can't use real rocks because they're too hard and the velocities available to us are too slow. So what we're going to do is use these special lightweight rocks, which were made for us by Ryan Johnson, a special effects artist. Ryan, can you tell us about these special lightweight simulated asteroids?
Sure. So these props that we've developed here are a foamed plaster type material that we use to simulate real rocks in movies, films, and things like that. Whenever we want something to break that looks like it's hard, this stuff breaks really easy and it crumbles. So what we've done is we've taken this same material and we've developed a much larger one we're going to use to simulate an asteroid. So we've got 2 of these, and we'll smash them together really hard, and that'll hopefully simulate the collision of an asteroid.
So what sort of speed do you think we need to smash them together so they'll break?
We just need to drop one on top of another from a reasonable height, and something like that.
Okay, let's try it. Let's drop the plum.
The distance of the drop is about 18 feet, which will give the falling asteroid a speed of 37 miles per hour.
A little bit more. Perfect, perfect right there. Okay, Ryan, we're ready for the drop.
Okay, it's pretty windy, but we'll see how we do.
All right, that is excellent.
Great.
Okay, I would say that's a success.
Thanks. Yeah, that's good.
Yeah.
It's amazing how much it's like really spread out.
Right, so in the asteroid belt, all these pieces would gravitate back together and form a rubble pile, what we would call an asteroid today.
So if they're starting to come together all the time, isn't that the same process that actually forms a planet? Why wouldn't the planet form that case?
Well, no, because then this thing gets hit again and again and again. So these things keep getting pulverized by impacts, and you're just left with little individual rubble piles rather than a complete planet.
Does this reasonably replicate what you think possibly an asteroid collision would be?
This is a pretty good analogy, in fact, because you get large pieces, you get dust, and so what we think are asteroids are basically rubble piles composed of these large pieces put together, covered then in dust. And so, yeah, I think you did a good job. This looks like the beginnings of an asteroid.
Great. Well, I'm glad it worked.
Right.
The asteroid belt isn't the only region in the emerging solar system where planets fail to form. At the outer fringes of the solar system, another ring of small objects orbits in frozen silence, the Kuiper Belt.
The Kuiper Belt is a region at and beyond the orbit of Neptune that has a whole bunch of rocky and icy objects pretty far apart from one another. Now, they were never able to coalesce to form a planet because there's just not enough of them close enough together.
50 million years after the solar system was born, both the Kuiper and the asteroid belts have 100 times more objects in them than they do today. These objects will play a monumentally destructive but vital role in the final evolution of the rocky inner planets, including the Earth. The inner planets take as much as 10 times longer to form than the giant planets outside the snow line. After 75 million years, the process is near completion. About 93 million miles from the young sun, the proto-Earth has reached planet size in a relatively stable orbit. But it has a cosmic stalker.
It's actually believed that the Earth was, in its early phase, accompanied by another planet, a protoplanet called Theia, which was actually in a similar orbit to Earth, essentially following roughly the same path.
For millions of years, the sister planets chase each other around the sun in a dangerous duet. But a clash is coming that will have immense consequences for the fate of the Earth. The making of our solar system has gone on for 80 million years since the collapse of the giant gas cloud that started the process. the inner planets have largely taken shape. But now, the Earth, which will one day harbor life, faces the potential of an early and cataclysmic death. For millions of years, Earth has been followed by the protoplanet Theia. The two bodies travel in essentially the same orbit, gradually coming closer and closer. Now, for Earth and Theia, it's crunch time.
The Earth-Theia collision early in the history of the solar system must have been a spectacular event. A Mars-sized object came in and hit Earth's side, splattering part of the crust and mantle of both objects into space, forming a ring of debris from which the moon then formed.
Having survived the cataclysm and gained a moon, the Earth settles in as one of the stable planets of the inner solar system. The drama now moves back to the gas giants, whose shifting orbits threaten to tear the solar system apart. At 500 million years old, all of the solar system's planets have been formed. But surrounded by debris in the planetary disk, they are on the move.
As waves of density are formed in the disk, the planets are almost surfing on the waves of material in the disk itself. You're really shuffling the deck completely from where planets are formed to where we finally see them.
In the early solar system, the three outermost planets as a group are closer to the Sun than they are today, and Neptune's original orbit is inside that of Uranus, the reverse of their current position. In addition, the asteroid and Kuiper belts each have 100 times more material than they do today. The small bodies of both belts are constantly flung around by the giant planets and their intense gravity. As massive as they are, the big planets react every time they toss a planetesimal somewhere else. The reactions may be small, but they add up to make the orbits of the giant planets migrate to new positions.
Early on, the outer planets tended to move around quite a bit. They migrated. Now, Saturn, Uranus, and Neptune sent planetesimals in toward the Sun. That means they had to generally move outwards. Whereas Jupiter flung planetesimals out to very great distances, even ejected them from the solar system, and that means that Jupiter had to move in.
What determines these in and out movements? They result from a law of physics that says energy is never lost.
When a planet ejects a planetesimal, the planet itself has to move in a little bit, and that's simple conservation of energy. It's giving a lot of energy to the planetesimal, dumping it way out there. That means the planet, has to move in. It loses energy. If an orbiting object loses energy, it's not moving as quickly. That means it drops to a lower orbit.
The amusement park, again, illustrates the forces at work. In this case, the slingshot effect. It's a gravitational boost that large planets can give small objects. In the 1970s, scientists exploited it to accelerate the Voyager spacecraft as it swung from planet to planet in the outer solar system. Here on Earth, we can think of the slingshot as a roller coaster over the edge.
The Boomerang roller coaster ride that we have here is a nice example of the processes that are involved in the slingshot effect. The gravity here that makes this work here on Earth is using Earth's gravity. It pulls down on the cart, and it pulls it down the slope, and then the cart goes back up the slope due to the momentum it gained from coming down the slope. What if we were to add Jupiter to the system? Now Jupiter's gravity will still pull the object in, but Jupiter swings it around the planet, and it goes around Jupiter, and the motion of Jupiter gives it an extra kick, so that it gets more momentum than it came in with, and gets shooting back up the slope and out into space.
millions of small gravitational tugs have made subtle changes to the planetary orbits for more than 500 million years. Earth and the other young planets may settle into conditions conducive to early life. If so, it's about to be wiped out as the gas giants Jupiter and Saturn reach a remarkable tipping point called a resonance.
As soon as Jupiter and Saturn hit the resonance, it was catastrophic. The entire solar system flew apart in just 1 million years, which is a tiny amount of time compared to the age of the solar system.
The resonance means that every time Saturn orbits the Sun once, Jupiter will go around twice. The result? Jupiter and Saturn come very close to each other in the same part of the solar system on a regular, ongoing basis, creating an immense gravity pump.
It's like pumping a kid on a swing. If you hit the kid on the swing at just the right time, you can get the motion to go higher and higher and higher.
The most dramatic effect is on the two outermost giant planets.
As all of the planets were orbiting around the solar system, having gravitational interactions with each other, one of the most amazing things that happened is that Uranus and Neptune actually switched places. So now Neptune is farther away than Uranus.
The resonance is a cataclysm whose effects sweep through the system at astounding speed, not only shifting orbits, but clearing out most of the system's small objects.
Jupiter alone is quite a gravitational bully and gradually depleted the asteroid belt. But the Jupiter-Saturn resonance caused a catastrophic depletion of both the asteroid belt and the Kuiper belt.
99% of the bodies in the asteroid and Kuiper belts are cleared. While most of them are thrown out of the system, some of them plunge inward. Drawn by the gravity of the Sun, they rip through space toward the inner solar system. How will the inner planets, including the Earth, escape the onslaught? The making of our solar system reaches a violent climax 700 million years after the pre-solar cloud first began to collapse. And Earth is in the firing line. The gravitational chaos of Jupiter and Saturn is battering the inner solar system's planets and moons in an event now known as the Late Heavy Bombardment.
A lot of the material in the outer solar system, these comets, fell in towards the inner solar system, where they collided with the inner planets and the moon, creating the craters that we see today.
Some researchers believe collisions may have repeatedly sterilized the Earth, and that if life had formed, it was wiped out and had to start anew. But the impact of objects from space, along with their violence, may have also brought a benefit.
The Earth might not have all the water it does today had it not been bombarded by material from the outer solar system. Some have speculated that much of the water we have on Earth is actually a result of impacts from the late heavy bombardment period.
Today, 4.6 billion years after the solar system's birth, the ongoing, if remote, danger of a massive asteroid strike means the story is not over. More important, though, are the hundreds of tiny asteroids hitting the planet as meteorites. Studying them tells us if the making of the solar system really happened when and how we think it did.
I'm holding a sample of the Allende meteorite. The Allende meteorite is a fragment of rock that fell in Mexico near the village of Allende in 1969. One of the components of the meteorite are these calcium aluminum rich inclusions, these white objects that you can see on the surface. These are the oldest known materials in the solar system, and we know this by age dating with radiogenic isotopes.
In his high-tech lab at UCLA, cosmochemist Ed Young and his colleagues carefully examined tiny samples of ancient meteorites.
There's a big white fragment in the middle, which we want to cut out.
The lab's precision lasers aim at the fragments, blasting out holes no wider than a human hair. Sophisticated analysis measures radioactive elements, which serve as atomic clocks. In early 2011, cosmochemists in a similar lab at Arizona State University dated part of a North African meteorite to an incredibly accurate 4.5682 billion years old. The oldest material ever found on Earth, older than the planet itself. In August 2011, the Dawn spacecraft arrived in the asteroid belt, source of most meteorites. Close-up pictures of Vesta, the second largest asteroid, open a new epoch in telling the solar system's story.
One of the exciting things about the Dawn mission is that we're going to get our first glimpse into something that was essentially a mini planet that was formed right at the beginning of the solar system.
Since its birth early in the solar system's history, Vesta has been undisturbed by weather or many of the geologic forces that have changed the planets over time.
Just like some of the larger planets, it has volcanoes, it has a core, but unlike these larger planets, not much else has happened to it in the past 4.5 billion years. So we essentially get a window back into that very earliest history of the solar system.
Dawn will orbit Vesta for a year before going on to spend another year orbiting the largest asteroid, Ceres. Meanwhile, NASA's Juno probe has just begun its voyage to Jupiter, where it will visit the giant planet to determine if it really does have a solid core and formed early and quickly, as scientists now believe. Even more crucial are other stars with their own solar systems whose formation sheds essential light on our own.
The most important reason for understanding how the solar system was made was to find out whether or not we're normal. When you look out and look at other solar systems being made with our telescopes today, for example, in Orion and other places, we want to answer the question, how normal is the solar system?
Launched in 2009, the Kepler mission is now running full blast and has identified 1,200 possible planets around other stars. Some systems have Jupiter-sized planets close to their suns or in lopsided orbits. Others have only small planets crowded closely in the hot zone of their stars. Our solar system, however, has its planets in near circular orbits, spread out in a stable arrangement that seems almost too perfect.
One of the great surprises of the last decade, as we started to discover other planetary systems, was the fact that our solar system seems to be one of the oddballs, most because our own solar system is so regular.
Is the solar system made by processes that we can observe going on today, or are we somehow special? This goes to the point of whether or not life is special.
And that question is perhaps the most important one of all, as the life story of the sun and its planets essentially becomes the life story of life itself, humanity on Earth, and our ultimate place, alone or among many, in the universe.